Welcome to this course on distributions and Sobolev spaces. This is first part of our proposed advanced course on PDE. In this lecture, we will collect some results from measure and integration theory, which is a prerequisite for this course, but for the benefit of the students, we are going to collect some results from measure and integration theory and introduce also in the course notations and other objects which are used throughout in this course. Okay, so let me begin with this notation. So for so omega is an open set in Rn bounded or unbounded, that does not matter for the time being, and for 1 less than or equal to p less than or equal to infinity, Lp omega denotes the space of all measurable functions defined on omega for which this integral mod fx dx omega to the power p mod x to the power p is finite. So, this is for p less than infinity, and for p equal to infinity. So, this is essential supremum of mod fx x in omega is finite. So, many of the results, okay, so here so we are always dealing with the functions can be either real valued or complex valued. So, I am not going to say that repeatedly, and our integrations are always with Lebesgue measure on Rn. So, those things are understood, and in Lp omega we introduce this norm. So, this is the notation. So, this is, let me write it one more time, mod x fx to the power p dx to the whole power 1 p if p is less than infinity, and the L infinity norm is the essential supremum of mod x in omega. So, many of the results we are going to state are valid only for this range, and some of the results may not be valid for p equal to infinity case. The main reason being that the space L infinity is not separable. Okay, so, this abstraction makes many results which are true for other LP spaces, whereas this LP is separable for 1 less than or equal to P less than infinity. So, in the early part of a course on measure and integration, we learn about 3 Littlewood principles. So, one of them is okay. So a measurable function is almost continuous. So, this is more precisely stated and proved in a theorem. So, it is called Lugin's theorem. So, you may recall this one. So, this is a good time for you to recall what all you have studied in a measure and integration course. This is Lugin's theorem. So, this makes the above statement, namely a measurable function almost continuous, is stated in this Lugin's theorem. Okay. So, using Lugin's theorem, and other technical things, what we can actually show is, so for okay, this, let me just state this CC omega, okay, okay. So, this is the space of continuous functions having compact support in omega. So, in general support of a function, so just let me just say that. So, if f is a function defined on any set, any omega, okay. So, since we are dealing with omega, so let me just say that support of f. So, this is the set of all x in omega for which f x is not 0. This is true for any function, and you take the closure. Okay. So, this is always a closed set. So, in addition, if it is also bounded, so then we say that f has compact support. So, that is the, so this some authors also use, instead of C, they also use this one. So, okay, that is just notation. Okay. So, Lugin's theorem and other little technical results, they show that. So, this is, I would say it as a theorem. CC omega is dense in LP omega one less than or equal to P less than infinity. So, this is not true for p equal to infinity. Okay. So more precisely what we can write this in expansion form. So if f is in LP for this range, so there is a phi in CC omega such that the norm f minus phi is less than epsilon. Okay, so for a given epsilon. So for a given epsilon, we can always approximate in the norm the given LP function by a continuous function with compact support. Okay. So in other words, so if you take epsilon equal to 1 by n and let that 1 by n to infinity, so that's a usual statement of density. So if f belongs to LP, both are same, there exists a sequence phi k, because n we are using for the dimension. So CC omega such that f minus phi k again in the norm tends to 0 as k tends to infinity. And using this result, now we are going to show that in fact this is just continuous functions. So even infinitely differentiable functions are dense in LP. That's what we are going to show. So this has many advantages. So let me just state couple of things where such density results are used. Okay. So let me state this as a fact. Okay. But this need to be proved. Okay. Okay. So this so if f belongs to LP omega, so when I don't mention the range of p, so avoid that p equal to infinity. So p equal to infinity, you have to consider it separately. Okay. So then integral omega f of x plus h minus fx power p dx tends to 0 as mod h tends to 0. Okay. So this, so extend, since there is f of x plus h, so this is easily done. Extend f outside omega by 0. So that means if x does not belong to omega, so you put f of x equal to 0. So this is referred to as continuity in the norm. So this is very easily proved by the density theorem we just mentioned. So if, for example, if f is a continuous function with compact support, this result follows very easily by the uniform continuity of the function f, and general case follows by density arguments. Okay. So you should get used to such density arguments which are routinely used throughout this course. Okay. Another fact, so if omega is unbounded, so in particular if omega is Rn. Okay. Then you consider this integral mod fx to the p dx. Where do you consider? So, the domain of the integration here is omega intersection mod x bigger than r. Okay. So, this is the exterior of the sphere intersected with omega. So, if omega is bounded, this eventually this integrand becomes 0. So, then this whole integral is 0, but the general thing is even when omega is unbounded. So, this goes to 0 as r goes to infinity. Okay. So, again this result is easily seen when f is continuous and has compact support. More generally if f has compact support and in LP. So, because then for such functions when r is large enough, this domain of integration is empty. So, automatically it becomes 0 and then the general case follows from the density argument. Okay. So, these are the consequences or usefulness of the density theorems. So, more smoothness still better. Okay. So, that is what we are going to see. So, to see that C infinity functions with compact support are dense in LP. So, we need the concept of convolution. So, this is another important tool we are going to use in this course. Okay. So, if f and g are in L1 Rn, the convolution so this of f and g denoted by f star g is defined by f star g of x again this integral is over Rn. So, f of x minus y g of y dy. So, in a moment we will see that this integral is finite almost everywhere, and that is a consequence of Fubini's theorem. And so, this one by change of variable we can also write this as f of y g of x minus y dy. Okay. So, that is nothing but g star f. Okay. So, this operation of convolution is commutative. Okay. And this is defined for all f g in L1. Okay. So, this again you recall. Okay. So, this it is a consequence of Fubini theorem which deals with interchange of two integrals. consequence of Fubini theorem that F star G is in L1 of Rn, and we also have this estimate F star G in L1 is less than or equal to F in L1 G L. Okay. So, it is interesting to note that in general product of two L1 functions need not be L1. So, in particular, okay, so just so since F star G is an integrable function, in particular F star G of x is finite almost everywhere. In fact, the hard part of this theorem is, just let me mention that the hard part of this, you might have already seen it, hard part of the proof lies in showing so this function, showing this function of two variables. So, this is in R2n going to f of x minus y g y is measurable. So, once we establish this measurability, the rest is taken care by the Fubini's theorem. So, this is interesting in the sense that in general the product of two L1 functions need not be an L1 function. Okay. So, this an example. So, in that way this convolution becomes an interesting object. So, if you take f equal to g equal to 1 by root x, the characteristic function of 0 1. So, this is in n equal to 1 on the line. Okay. So, f and g are in L1, but f g the product. So, this is in L1, but f g is 1 by x, the characteristic function. So, this is not in L1. Okay. So, this convolution also makes the operation little smooth. Okay. So, that is another example. I will just so you should work out these examples. So, again you take f equal to g, the characteristic function of minus 1 1. So, again this is n equal to 1. Okay. So, just let me draw this. So, this is your f. So, this is minus 1 1. So, this is 1 here. Okay. So, obviously f and g are not continuous at these points. Okay. So, you just work out this one. So, f star f. Okay. So, instead of writing the expression for this function. So, let me again draw the graph here. Okay, so, this f star so this minus 2 to 2, so this is 0 and this is the function. So, this is straight line and again 0. Okay, so, this is 2. So, f star f is continuous. Okay, so, that is the thing I want to indicate. Okay. So, again some simple properties. So, just I will mention. So, you can work out more details. So, this so support of f star g, okay, so is contained in. So, this is very easy to verify, support of f. So, the plus support of g. So, right hand side is sum of two sets. Okay. So, in particular if f and g have compact support, so f star g also has compact. So, in f and g have compact supports, so is f star g. So so has. Okay, so that's and there are more general results. So we recall this one. So we just defined the convolution only for two L1 functions, but this is a more general result. Okay, so just let me state that. So if f belongs to LPRN and G in LQRN, so now you can have any range. So I just put it here 1 p less including infinity. So that's no problem, but only condition is that 1 by p plus 1 by q is bigger than or equal to 1. So we can write that as 1 plus 1 by r. So then f star g is in LR Rn and so this f star g in R norm is less than or equal to f of p g of q. In fact, we can reduce this general result to the case of two L1 functions by appropriately taking the powers. Okay, so that's a more general result. Okay. So now we are going to use this notion of convolution in order to show that the space of C infinity functions with compact support are dense in LP. Okay, so that is our next topic of discussion. So, this is modifiers. Okay, so that is our next discussion. Okay, so so define. So, this notation we keep throughout this course, rho from Rn to R by rho of x is equal to some constant exponential of minus 1 by 1 minus mod x square if mod x is less than 1, 0 if mod x is bigger than or equal to. Okay. So, it can be verified that, okay, so verify. So, this is rho is actually a C infinity function Rn, and support of rho is precisely B01 closure. So, this is set of all x in Rn. So, that is notation. Okay. Mod x is less than or equal to 1. So, this is the Euclidean norm. I did not mention that. So, this is just Euclidean norm. Okay. So, this positive constant is chosen so that the constant C is chosen so that integral rho of x dx is 1. Note that the support of rho is this closed unit ball. So, this domain of integration is only that compact set, namely closed unit ball, and rho is a continuous function. So, this is always a finite number. Okay. So, if you just integrate this exponential thing, and so we are choosing this constant C so that this integral becomes 1. Okay. So, in order to verify that rho is a C infinity function, if you have not done it earlier, okay, so I will suggest that you first work out this one dimensional example. So, let me use a different. So, phi x is e to the minus 1 by x square if x is positive, and 0 if x is less than or equal to 0. So, then phi is infinity. So, it does not have compact support, but it is a C infinity function, the same arguments. So, here we need to check only when at x equal to 0. Otherwise, at all other points the smoothness of phi is very clear. So, only thing is we have to verify that it is also smooth at x equal to 0, and once you do that thing, so it is easy to show that this rho is also C infinity function. So, we have to verify only at the points where mod x is equal to 1. Okay. So, we will now see in the next lecture how this rho is used in order to show that C infinity functions with compact support are dense in LP. Thank you.